Hi guys, and welcome to this very exciting tutorial. Why very exciting? That's because we're about to get the final outcome of the dream. Right now, by building this variational autoencoder, we're basically making an artificial intelligence dream, and right now we're about to implement the decoder part of the VAE, which will decode the latent vector z obtained stochastically to reconstruct the input images that our same AI was able to see thanks to these 4 convolutions here. So that's pretty a big deal. This is actually the first time I am implementing an AI that has the ability to dream, and actually this is the first time for anybody in 2018. So let's celebrate this special moment. We're about to make an AI dream with the decoder part of the VAE. So here we go. In order to make that happen, we have to implement everything from here to the final reconstructed images, which has the same dimensions. And so the first thing we have to do is another fully connected layer. Alright, so let's do this. Let's go back to Python and let's create this. Let's add it in the full architecture of the VAE. And since this is going to be basically a new hidden layer, we're going to call it H again. And H is going to be a fully connected layer, which we can get again by calling TensorFlow, then by calling the layers module by TensorFlow, and from the layers module, we call again the dense function. And so this dense function, exactly as here, is going to take 3 arguments that we need to enter. The first one is the input vector to which this new dense layer is going to be fully connected. And of course, as we can clearly see in the architecture, is going to be Z, the latent vector we got in the previous tutorial. So let's enter this input, self.z, as it is a variable of our object. And then remember, the second argument is the number of units in this dense layer. And as we can clearly see here, it's going to be 1024 units. Don't worry about the 1 times 1 times here. This is because we'll need to reshape it, but we'll do it right after that. First of all, let's get these 1024 units in the second argument, 1024. All right, and then as a final argument, we can give a name to that new layer, this new fully connected layer. And since it is indeed a fully connected layer, we're going to keep the FC here. However, since we're now dealing with the decoder, I'm going to replace enc by dec. And then I'm going to remove the mu, because now we're simply dealing with a simple fully connected layer. Alright, so basically that smashes the first step of building the decoder, that is this step here, getting the new fully connected layer. Then we have to do this reshape here to get indeed a one-dimensional vector of 1 by 1 by 1024 dimensions with 1024 elements. So the way we're going to do this is by updating H again, and then as we did before, we're going to take the reshape function by TensorFlow. Here we go. Then first we need to input what we want to reshape, which is H, which right now is just a fully connected layer. And in order to get this one-dimensional vector in a one-dimensional batch and composed of 1024 elements, well, we're going to do kind of the same thing as what we did here, but this time there's going to be 2 more dimensions, which are corresponding, of course, to these dimensions here, 1 by 1. So these new dimensions are just to be 100% aligned with the format of the future reconstructed images, because in order to reconstruct them, we need to have the right dimensions for the future inverted convolutions. So we're just getting this format by creating these additional dimensions so that we can apply then the inverted or transposed convolutions. All right, so let's add these new dimension here, 1 by 1. Here we go. And now we can just keep the same, or, replace that by 1024, because indeed that's the number of elements we want to get in that one-dimensional output layer. All right, so now let's move on to the next step, which is finally the start of the deconvolutions, or more correctly, the inverted convolutions. So we're going to still update H the way we did here, and we're going to get TensorFlow, of course. Now from TensorFlow, we're going to get the layers module, because it is in this layers module that we'll find what we need, that is the conv2D transpose function, which will do exactly this inverted convolution, taking as input a one-dimensional vector in a one-dimensional batch, and then recreating some images, which we're going to do with several inverted convolutions to reconstruct the final images. So I've prepared for you now the conv2D transpose function by TensorFlow, but we can see that the arguments are kind of the same. They have the same names, same inputs, filters, kernel size, stride, padding. So they are the same, and therefore it will be a piece of cake to implement these inverted convolutions. All right, so here we go with the first one. The first inverted convolution is, let's go back to our world models article. The first inverted convolution is going to be an inverted convolution with 128 filters of size 5 by 5. So let's input that exactly the same way we did for the basic convolutions. First, let's not forget to, of course, input the input tensor, which is, of course, h, right? Which so far is just a one-dimensional vector. And then that's where the 128 filters come into play with a kernel size of 5 by 5. And then, again, we're going to have a stride of 2. And then, as we can see, if we look at it again, a rectifier activation function. So we can just actually copy this to be more efficient. Activation equals tf.nn.relu. And then eventually we can give a name to that new first inverted convolutional layer. And here we go. We're going to call that this time, well, first not enc, but dec, and then not conv, but deconv1, right? The first deconvolutional layer. Let's call it this way. All right. So now is going to be the real piece of cake, because to create the other inverted convolutions, we'll just copy this and we will paste it just below, just like that. And now, of course, we don't have to replace the input because it is keeping updated like a domino, but we have to replace the number of filters and the name here, because indeed we're going to keep the relu activation functions and the same kernel size. So let's see. In the previous inverted convolution, we had 128 filters, and now we're going to have 64 of them. So let's put that right here in the second inverted convolutional layer, 64 filters. And then deconvolution 2. All right, and then let's paste that again. We can guess the new number of filters, which is going to be, of course, 32, right? 32 right here. But be careful, a new kernel size of 6 by 6. I didn't catch that before. So let's this time replace 128 by 32 and 5 by 6. All right, pretty easy, right? And then deconv1, we replace it by deconv3. And now I'm going to copy this because I want to lower my chance to make any mistake. Paste, and what is going to be the final number of filters in the last inverted convolution, right? This is the last one here. We're getting so close to the reconstructed image. We have to make first the final inverted convolution, and this one has only three filters of size 6 by 6. So let's implement that right away. 3 filters and a kernel size of 6. Perfect. Then, final thing we have to do is to replace the name dec_divconv3 by dec_divconv4. However, now, since this is actually the last convolution, it is not a hidden layer anymore. It is the final layer, and also, wait for it, the final reconstructed images. And that's why we're not going to call that h, but self.y, which is a new variable of our object that we're introducing, and which is, of course, the final output of this whole convolutional variational autoencoder. But now be careful, as most of the final layers, the activation function used is not a rectifier activation function, but indeed a sigmoid activation function. You will see that in most of the artificial neural network architectures, whether it is a fully connected neural network or a convolutional neural network or even a recurrent neural network, the final activation function used for the output layer is a sigmoid activation function. So we're going to replace that ReLU activation function by the sigmoid one, which is also available from the neural network NN module by TensorFlow. And now everything is all good. Congratulations, you have just given an artificial intelligence the ability to dream.